Hi, and welcome to another edition of shading. This is general purpose shading knowledge here, and my name is Nate Nestler, and this is for Hyperactive Studios. Now we're about to go over light models, which are a little more, when we start getting to more of the advanced areas of shader programming, because we start calculating how light interacts, and these are very simple light models. So as far as the light models go, these are like the baby ones, but they're core, and they're the main ones that are used on a regular basis. Once you know this, then you can start going into higher and higher areas where you're doing more and more advanced shading. But this is a good basis platform to start from in order to move into the more advanced shading capabilities. Alright, so let's look at some algorithms, and let me just real quickly execute all the cells. So I'm going to evaluate all the cells, and bam, there they go. Alright. So, the only thing I don't like, I put it in this order and rearranged it to this order. Typically, you're going to have, I ambient times Ka, which is your special variable for ambient that's artist controlled. Well, let me just show you right here. I have a write-up for each part here, so not to leave anything to the imagination. But this is the Lambert shader model, and one of the cool things about this is once you have the Lambert shader model down, then you can also use the same model and then you just add Specular in order to get the Phong shader model. So it just kind of builds on each other. You'll see that a lot with the other light models too. They're just different variations of different algorithms in order to create different effects, which is great. Okay, so IP is going to be, think of it like your point on your surface or some position, if you will. Total light calculation per point in the model. This could be per fragment if you are doing a fragment or lighting model instead. Now remember, you can either do vertex lighting or you can do fragment lighting. Fragment is far more computationally intensive because you're doing it per pixel and not per vertex, so big difference there. Vertex lighting can be much faster. This completely depends on if you are implementing the algorithms as a vertex shader or a pixel fragment shader, so it's totally up to you which way you use it. Ka is going to be your ambient lighting variable that fills in the shadow areas with a certain color from the artist here. This should be an artist usable parameter in the shading interface. Yes, the Ka, or you should just say call it ambient color to the artist. But you should always have that available in your interface when you're having the artist work with it. And what I mean by that is, like, say for instance I'm inside here in this FX composer here, right? So say I'm in here and I don't know, I'll select one of these. Alright, so I got this code or whatever here. You'll notice that I have ambient color, and that's referring back to my Ka, and I can just basically click this and have a artist usable controller set up. And you can see actually how it affects that shader as we move it. So that's how that variable actually applies. You can see it actually shading in those other areas there, or the ambient portions of the model. It is not the main color, as you can see. It's more like the fall off shadowed area there, if you will, as it starts to recess into shadows. So there's that. Now the diffuse color is going to be your main color. Now if I start manipulating this, you can see that yes, indeed, it absolutely affects this main color here. I also have it be multiplied times the texture, which you'll learn about later on if you take the CG series here. But let's pull this back up. That gives you an idea of some of these terms here. So now you know what diffuse is. Emissive means glow. It's going to make something glow. Well, I could show this, but basically it's just going to make actually they probably have it in the shader library and just show it to you. You have something kind of like that. There's glow. God rays doesn't really glow. That's balloon glow, which doesn't really look like glow to me. Let's see here. I'm trying to find a better example. They got them on here, just a matter of finding it. That's radial blur. It's closer to like what glow looks like. I've seen it a bunch of times. All kinds of stuff glows in games. There's glow. That's definitely glow. So you got this glowing stuff going off the edges there. And so you got a good idea of what glow is. Here's a good example of it here. So on and so forth. And you got some glow going on this one too, etc., etc. And it can be image based. There's lots of other examples I could use, but that gets the idea across. Okay. Now, going forward here, besides emissive and diffuse, there's also specular, and this is for Phong here, and this is going to be the shiny highlight. So, as a real quick example, you see like the highlight here? Let me change that from Lambert to something like Minart, and let me change this to Word ISO, and now you can really see it. So that right there, that little white spot there, that's the highlight, or just like the highlight on the surface here of this glass here. See how I've moved this around here? We get this highlight on there. That would be the specular. Okay, cool. And here's a graphical representation of it here. Let me remove some stuff to make it simpler right now for Lambert shader. That's Lambert shader right there for the this is the normal coming off of the surface of vector, and then this would be your light vector here, point direction from your light as it hits a point on the surface. Now if you have many lights, like I do here, but I didn't bother to go through the trouble of replicating this, but you'd actually have multiple directions here going from the light from every direction of every light. So for all these lights, I'd literally have another L direction vector occurring for each light, and then the summation of these lights would be the overall lighting contribution to the surface, or shall we say, in simple terms, basically all the lighting combined ends up shading this surface. That's all there is to it. And just get that a little more accurate on that point there. Sure. That's a little nicer. Just a little. There we go. Alright. Sorry, I'm picky. Alright. So, there's our specular. And then when you add them all together, then you can apply it to the surface color of the shader itself. So this ends up being your overall shader color, if you will. Of course, you can also add maps, and there are multiply them times these different values for textures or something like that. So this wouldn't have to necessarily be the end-all result here, because you could literally sit there and do additional manipulations. This is just from the actual light value itself, and you get the overall lighting contribution. You can individually manipulate each one of these channels separately for specular, or and thereby multiplying a texture in there to modify them, which is very useful, by the way, and especially something you would be very interested in for artists. So, by all means, check that out. Alright, so that's a little bit of a breakdown of the different parts there. Let's have a look at some more of this. KA again was our ambient lighting variable that fills in the shadow areas, as I showed earlier, with a certain color from the artist. This should be an artist's usable parameter in the shading interface. I just said that earlier. Dealing with this one right here, remember when I sat there and manipulated this color here. So remember, that is our KA. Don't forget KA right here. Awesome. Alright. Now going back over here, we have our IA, our I ambient. This is the incidental light ray for our summation of all our lights here, basically. Like I was just showing earlier. You get the idea. This variable controls the ambient lighting. It can also be a summation of all the lights. There we go. So that'd be the amount of contribution of light from all the different lights. KD equals diffuse lighting variable. That is, remember, KD is your diffuse lighting color. So if I'm sitting here, let me go back to this one real quick. So if I'm in here and I'm moving this around, remember, this is the diffuse one. So this is your main color driving parameter here for the artist. And that's essentially what it is. It's just easier to show graphically than to wrap some explanation, but basically that's what it is. But this will be the main point of light on the surface of the model for its diffuse overall shading contribution. This is an artist controllable variable that should be in the interface. And like I was just showing you how I had it in the interface, that's what you need to have for the artist too. And of course, if you're taking the CG training series, you'll learn about that. Also in the OpenGL training series too for the GLSL shading. Alright, so ID, incoming diffuse light color intensity. Alright, so that's exactly what it says. It's the incoming diffuse light color intensity ray vector. So N and LM are both normalized, so that's important to remember. They have to be normalized. Do not overlook that. Just because you have a normal on the surface and you don't normalize it, you're going to get really bad results if you don't do this. So it's absolutely vital that you only have the direction of the normal and none of the magnitude. So the normalized surface normal, it's just like, well, we've talked about normals a bunch now. You will sometimes see N as having the a hat over the top of it, so you'll have like N hat here, as it's called, because it calls the hat sometimes in mathematics, over its head because it has been normalized, and that's a good way to denote that something's been normalized. And also, you'd have a hat over LM too, by the way, because it's been normalized too. LM is the normalized vector that goes from the point on the surface to each light source. Now, I showed this a second ago over here in Blender. And you can see here we have the normal of our surface going straight up. Now, you can have bitangent normals going, off in different directions, but for this we're just going to say that this is just simple shading here method with our normals, and we only have one normal and it's facing straight up for this particular point. Okay, cool. And here's our vector going to our light. So that's involved with our light, and we're going to dot these together for our dot product in order to find the result. So let's have a look at our algorithm here. So we do our light calculation for our point on our surface here as IP equals KA. Remember, KA is the artist controllable ambient lighting times I ambient, which is going to be our lighting summation of lights, plus sum, or ESUM here. This is normally written out as the ESUM when I showed you ESUM over in another video, and the ESUM goes from one set values to another. So in this case, it's going to go from 0 to the number of lights, and that's how the summation is going to go. And then we're going to have here KD, ID, KD. So you're going to have your diffuse channel times your incoming diffuse light intensity ray here times value. Not ray, but sorry, value. That's not array. That's just a solid value. And here we are going to have our normalized vector dotted with our light vector coming from the light source here. And with that all computed up, and again we're doing this across every light, so this is going to be done across all the lights until we get our final result. So we'll just keep looping until it's done, and so you end up with all the lights being computed this way, and so you get the final contribution of all the lights applied to that particular point on the surface. So you can see why vertex lighting is going to be way faster, because you have far fewer vertices than you do fragments or pixels. So it makes a massive difference. Okay, so that is the Lambert shader. Now we can break this down to its parts. The ambient is nothing more than Ka times I ambient. That's all the ambient is, and that's the entire ambient contribution. Of course, emissive is nothing more than Ke is equal to emissive. Diffuse is equal to Kd. Remember, that's our artist control for our diffuse channel here. Remember, artist control, diffuse channel color. This is our diffuse. Remember, ambient. Sorry if I'm beating a dead horse, but I'm trying to get it in your heads. Alright, so there's our ambient. And here we have our, and then for the diffuse, like I was saying a second ago, KD times ID. Of course, ID is going to be your incoming diffuse light color intensity, and then times N dotted with L. N is your normal vector, L is your light vector. So that gives you your diffuse light, and that's what that whole part was. Has the E summation done on it. Alright, and then our specular goes back to our Phong shading here. So we have our KS, this is our specular. It's the hot highlight, remember, on the surface here. So if I had, what was it that I made so bright? Oh, it doesn't matter. I'll just change this one real quick and make it. It's that, hot white spot right there on the surface of this model. That is the specular. And the tighter it is, as you can see, the shinier it becomes. And the lighter it is, or lesser it is, the less of an impact it has on the surface. So be aware of that. Changing some things around can make this tighter or less tight for the actual specular here. So it makes a difference, that's for sure. Okay, and R is a reflected. Okay, so back over in Blender, let me turn on the other rays here. So R is our reflected vector coming back from the surface here back towards the camera. V is going to be our view direction vector, as we have going from the camera to the point on the surface. And the angle between V and R, or right here is RM, is for reflected method on here, is the actual shininess. So depending on the angle, it's going to depend on the shininess of the surface. Alright, so that's very cool. And so that's what we're getting into here. We have R dotted with V here, and then it goes to the power of the shininess. Now, I got some very nice information on this. Phong shader broken down with all these parts of the specular broken down here too. Let's just leave it like that. Okay. So this is Phong shader is the Lambert shader from above that we have up here, plus the specular here. So let's see what we end up with. KS again is the artist controlled specular color I just showed a second ago. This should be implemented in the artist interface. IS is incoming light intensity color of the specular. V is the eye viewer direction vector, also known as camera. That's why I have the camera over there. You can also think of this as a camera in the scene if that is confusing. RM is the reflectance vector ray that reflects or points back towards the eye viewer direction as a normalized vector. It points back towards it, but it's not necessarily aligned with it. If it's totally aligned with it, then our angle of shininess is 0. Shininess, the angle as cosine between V and RM. When the value is high, then it will cause a near mirror-like reflection. So basically, the further apart these two vectors are, here between these two vectors here, the larger the angle is going to be, so the greater the shininess. Okay. Alright. So when the vector is high, then it will cause a near mirror-like reflection, resulting in a very small specular. When this value is low, then the specular will become quite large, which will result in a far less shining surface. So as that angle shrinks, the larger the specular is going to be on the surface. Okay. So we have our IP equals KA. So this is the actual Phong shader with all parts applied to it. So we have our Lambert plus our specular here, basically. So we have Ka times I ambient. Remember, Ka is our what? Our ambient artist controlled variable. IA is going to be our value for our overall contribution of light, plus the summation of KD times ID times N dot LM for all number of lights, plus the specular here of KS times IS, where KS is our specular artist controlled, IS is our incoming light intensity color specularity. Same thing here with ID too. ID is your incoming diffuse light contribution here, And then our KD is our artist controlled diffuse one. Don't forget L is going back to the light here, and N is your normal. So right here we have our KS times our IS times our RM, which is our reflectance vector, dotted with our viewer vector, our I vector if you want to call it, or you could call it the camera vector, however you want to call it, to the shininess, semicolon. Well, you don't have to have semicolons though, really. Well, yeah, so if we're doing CG or GLS, it would be semicolon. So, yeah, I guess you do have to have a semicolon. But get the idea. This is I can't think of the name of the language right now. This is written in Lisp, I think. Yeah, I think it's written in Lisp for this. But there we are with our whole algorithm for our Phong shader. So with that covers Phong shading and Lambert shading as a general overall purpose, how to do how these algorithms work, and a breakdown of them. And this is really important to understand all these aspects of this, because if you don't have a good understanding or good grasp where this stuff is coming from, you may need to go watch this video several times before you get it down. Then you're going to have a hard time coding up these shaders, because without this understanding, you're not going to be able to code up a shader that would actually work for this. But we're going to go over 4 different implementations of the Lambert shader, with and without texture, for vertex and fragment. So, and both texture and non-texture for both fragment and vertex shader. So that's why we have 4 of them. We'll be going over that in our CG training series. We'll also be going over that in our GLSL series here. So, feel free to watch whichever one you're going for, and it should be quite useful to you. And we'll be implementing this hands-on. So, and then we'll move on to Phong after that. All right. So, with this covers overall shading light model theory here. My name is particularly for Lambert and Phong. My name is Nate Nesler, and this is for Hyperactive Studios. Thank you very much.